Hello and welcome to our first screencast. My first screencast. This is a bit of an experiment, so things may go awry. We may have bugs and issues or awkwardness that I can't control or I don't know any better how to control, and I hope you'll be forgiving of those issues. I'm at home, which means that we may have cats wander by the webcam, or you might hear my dog crying in the background. So I have to apologize in advance for those things, but hopefully we can have a successful session and that you guys will find this helpful. So we have two things we need to cover. So the first thing that we still need to cover is the Arrhenius equation. Okay, and you'll have to forgive my handwriting. I'm still getting used to using this tablet, not something that I'm used to using. And then the second thing we need to cover is called reaction mechanisms. Okay. Reaction mechanisms. So we'll cover the Arrhenius equation first. But before we do that, let's cover what we've already talked about in class a little bit, because I want to be able to relate those things to what the Arrhenius equation is. So we've been talking a lot about these things called rate laws, right? And a rate law talks about the rate of a reaction, and it relates it to something called the reaction rate constant. We'll call that K. There's a lot of K's in chemistry. To the concentration of each reactant, right? And then each reactant has something called an order associated with it, right? And that order tells us how changing the concentration exactly will change the rate, right? Where the rate constant, this K here, is like a proportionality constant, right? It's like what fraction of collisions are effective here. And then when we change the concentration, of course, that percentage, that proportion of effective collisions doesn't change, right? So these are the things that we've been talking about, and we've thoroughly discussed this thing called the order here, right? And we've learned how to figure out that order. But what we haven't really talked about yet is this thing here, this rate constant, K. So if I asked you guys to kind of think about for a second what goes into K, right? What is it that determines the proportion of reaction collisions that are effective, right? I don't think it would take you too long with some amount of pondering to figure that out. So the Arrhenius equation is really just an equation that talks about the things that go into K, right? So what is K made out of? What is this proportion made out of? There's three things generally that it's made out of, okay? So the first thing that it's made out of is something called Z, right? Where Z is the frequency, the collision frequency, right? The collision frequency, right? So how often do the particles actually hit, for a given concentration? That is Z. There's something else in K, and that is P, right? P is called the steric factor. Okay, and the steric factor, steric, that root word stare, same root word that's in stereo, means position in space, or arrangement in space. And the steric factor tells us what percentage of collisions are effective, right? Or what percentage of them actually collide in just the right orientation, right? Actually, that would be better. It's because there's a couple things that go into what makes them effective. So the steric factor is specifically talking about the percentage of collisions that are in the correct, oh, we're having one of those hiccups I talked about here, the correct orientation. Okay, that's what the steric factor is. And the third thing that goes into the rate constant, right, that determines the proportion of collisions that actually react, is the activation energy. So if you take a second and look at this small slide that I have open to the left here, this is an enthalpy diagram, which we've talked about in class, and it's showing the enthalpy diagram for two reactions, right? So this first reaction here that my cursor is going around has a larger activation energy, and this second reaction here has a lower activation energy. And you can see that if you imagine what's happening here is particles are colliding, and the percentage of particles that collide with enough force to get over this hill, over this activation energy, and make it to the other side, those are the ones that are effectively changing into products, right? So, of course, the percentage of particles that make it over that hill is going to be the rate. How fast that happens, how many and how fast is the rate. And for the bigger hill, there's going to be fewer that get over, right? So the third thing that kind of determines determines the proportion of collisions that are effective, is how big the hill is, right? So the activation energy. So we have this third term that's in K, and it's actually E, the natural number E, to the power of the negative activation energy over R, which is our gas constant, is what it's called, but it's really a constant that relates temperature and pressure and volume and number of particles all to each other in any equation, so we can use it for solutions as well. It's kind of this magical physical constant, kind of like pi, that's a part of the universe. And then temperature is here too, right? What is the temperature? So here it is. This is it, folks. This is the Arrhenius equation. It's just an expression of all the things that go into K, right? And I'll tell you that this Z and P are usually combined into a single constant called the Arrhenius constant, A, right? So the Arrhenius equation is K equals A natural number E raised to the power of the negative activation energy over RT. Okay, so that is the Arrhenius equation. So what the heck is this useful for, you might ask? Well, it's usually used exclusively to try and figure out the activation energy of a reaction, which is one of the things that you were tasked to do in the lab that we recently did, the thiosulfate lab. You actually had to use this equation. So how do you do that? Well, we're going to have to solve for activation energy, which is up here in the exponent, right? So since this is E raised to the power, probably the easiest way to get up here to solve for this is to take the natural log of both sides, right? So the Arrhenius equation, when you do that, becomes the natural log of K, right, is equal to negative activation energy over RT, right? But watch this. I'm going to leave that T out, and I'm actually going to separate it and put it over as 1 over T, okay? Plus, right, don't forget about this A. So when you take the log of two expressions that are multiplied by each other, then they become addition, right? So this is the natural log of A. And I hope that this looks familiar to you. It is, in fact, y equals mx plus b, right? So what do we have here? We have another, kinetics is full of these graphs that we have to know, right? We have another slope-intercept form. That is very useful because if we have a graph of a reaction and we at different temperatures, right? And we graph, let's make a little graph here. Ooh, there's another hiccup. I accidentally pushed the button, slid it. So we have a graph and we graph the natural log on the y-axis of K. And on the x-axis, right, our x is 1 over temperature in Kelvin. That's important. And of course, you have a negative slope here, right? You're going to get a straight line. And the slope of that straight line is equal to the negative activation energy over R, right? So what does a typical problem look like? And where you have to solve for activation energy? Well, you'll get a set of data of K's of reaction rate constants at different temperatures, and you graph them. And when you solve for the slope of that line, you're going to have to solve for activation energy and determine it. Okay. So actually, I'm kind of surprised that how common this question is, how much it's emphasized by the IB. Seems to be something that they like to give every year. So know it, get ready to do it. There is a question like this on your mastering chemistry tests to give you a little bit of practice. So go for it, and let's take a look at a quick example before we move on over here on this slide. So I'm just going to make this a little bigger so we can see it. Okay. So there's our Arrhenius equation. Okay, so here's a problem. Let's take a second to look at this problem. So you have the natural log on the y-axis, and you have 1 over t on the x-axis. It's already been graphed for you. So here's your graph, and of course, I hope you know how to solve for the slope of a line, right? If you have 2 points you can pick, and you do x2 minus x1 and y2 minus y1 to figure out this slope, right? So let's watch them do it. So there's our slope formula, okay, solving for the slope. And now that we know our slope, we can solve for activation energy, right? So here's the equation. And since our slope is equal to the negative activation energy over R, then what we have to do is rearrange this to solve for just activation energy. So it becomes the negative slope times R, right? And then this is what you end up with. And notice the unit is in joules over moles, and the reason for that is because the gas constant is in joules and moles, okay? So keep a note of that whatever your answer comes out in, it's in joules per mole, right? It'll generally be a very large because joules is a really tiny number. So you're always, for the most part, going to be converting that to kilojoules. And that's it, my friends. That is the Arrhenius equation and what it is useful for. So we can move on now to reaction rates. So let me just clear these notes here. Okay. And we'll do reaction mechanisms now. Okay. So, all right. I want you to consider, let me just find what I need to find here. Okay. Here we go. Okay. So consider this reaction. So NO2 plus CO yields NO plus CO2. Now, most students look at a reaction like this, and when I tell them, or when they think about it in terms of collision theory, because you've never been told otherwise, one thing you might assume is that this reaction happens in one collision. So pretty naturally, you might assume that this is a particle, a molecule of NO2, and here's a molecule of carbon monoxide, and this guy slams into this guy, and then you end up with the activated complex, right? It's some kind of like middle ground transition state that only exists for a second, right? And then they separate, and you're left with NO and CO2, right? So they collide, and then one of these oxygens gets ripped away, right? So naturally, that's probably what you think happens, right? Okay, well, if that's true, then the rate law should be affected by changing the concentrations of either of these, right? So if I add more particles of carbon monoxide, or if I add more particles of nitrogen dioxide, it's going to cause more of these collisions, right? So the reaction should happen faster. But it turns out when we look at this rate law for this, it ends up being rate is equal to nitrogen dioxide, second order, right, I forgot my K. We just spent all that time talking about K, and I forgot to put it there. And then carbon monoxide, it turns out, is zero order, which means it has no effect. Changing the concentration of carbon monoxide has no effect on changing the rate. And that just makes no sense when you stop to think about it, because if what's happening here is these two particles are colliding, then based on what we just learned with the Arrhenius equation, if we increase those number of collisions, the rate should go up, right? But no, right? So this is common in science, right? We think something and then we go and test it, and the results don't conform with what we think, and so we have to go back to the drawing board and figure out what's happening, right? That is the scientific process. It's the glorious thing about science. We're always trying to find the truth, right? So what is happening here? Well, we think we know. Scientists, I think, are pretty confident about this one, which is why we use it as an example. If you open any textbook on kinetics, this is usually the first reaction mechanism example that you see. And so this is what we think. We're not totally sure. You can never be totally sure. But what we think is happening is this. So this reaction doesn't happen in one step. It actually happens in two steps. So the mechanism, we call it the mechanism for this reaction. The first step we think happens is that one NO2 molecule, there he is, oops, I kind of drew over him, collides with another NO2 molecule. So this guy's colliding with himself in the first step, right? So he collides with himself, and the product that you get is NO3. It's an NO3 molecule, and an NO, a nitrogen monoxide molecule. Okay, so there's step one. Okay, so it's not that these two reactants are colliding with each other. It's actually that this reactant collides with himself first. Okay, so and then there's a second step. Okay, because if you look at that first step, it explains nothing so far, right? Neither one of, well, actually, yes, it explains the NO, right? It explains the nitrogen monoxide. But where the heck is the CO2 coming from, right? So we don't have an explanation for that yet. So this is what we think is happening in the second step. So what's happening is this NO3 here So NO3 that was produced in the first step is now colliding with the carbon monoxide that was there in the first place, right? And it is producing for us some NO2 and CO2. Okay? Okay. So that's what we're getting. All right. Now, I want you to notice, this is, if we're thinking of this in terms of first this and then that, like a series of linear events, right? Then what's happening is the NO3 is being created and then it's being used, right? Hence, why it does not appear in our overall equation, right? Because it is not a reactant, it didn't exist in the first place, and it's not a product. It doesn't exist in the end. And this arrow here doesn't tell us anything about what's happening in between, right? So NO3 is what we call, it has a name, it's called an intermediate. Okay? And an intermediate is anything that's created in one step and then destroyed in another. Okay? So NO3 is an intermediate. Also, notice that in our overall equation, we're only using one NO2, right? At a time. The proportion, all of the mole ratios here are 1 to 1, right? So this first step here is using 2 at a time, which does not really work with our overall equation, right? So how do you explain that? Well, you'll notice that in the second step, we're actually producing some NO2, right? So overall, in the scheme of things here, between the two steps, I'm going to cancel these out because they appear on both sides of the arrows. We're really only using one of the nitrogen dioxides, right? So if you look at our steps, when you add them up, right? So we'll add these steps up. What we get is NO2 plus CO yields NO plus CO2, right? What we started with. So there we go. There's our mechanism we created. And so how does this explain, you might ask, how does this explain still the fact that in our rate law, carbon monoxide has no effect, right? How does this explain that? Well, here's the deal. Each step in a mechanism has its own rate law, actually. It has its own rate law. And the rate law for one of these steps can actually be predicted, unlike rate laws for overall equations, right? For overall equations, you have to figure them out experimentally. There's no way to just look at the equation and know. But for individual elementary steps, that's what these are called. They're called elementary steps. Okay, so make sure you write that down in your notes, elementary steps. Each elementary step represents an individual collision event, right? It represents one collision that's happening, one event that's happening simultaneous, right? So these, in each one of these, you have one particle colliding with another. For each elementary step, we can talk about its rate law. So for this one, let me just change colors here. For this one, we can say rate is equal to, it has its own rate constant, okay? It has its own rate law, its own rate constant. Okay, rate is equal to the concentration of NO2, right? That's the only reactant here. And since there's two of them, we would say that it's second order. So in the case of elementary steps, the order does not have to be determined experimentally. It can be determined just using the coefficients, right? The number of molecules in the step that are colliding. So for instance, in this one, its rate law would be rate is equal to concentration of NO3 times the concentration of CO, right? So it also has its own rate law. And you might notice something funny here if you look at this for a second. You might notice that the rate law for the first step here is the same as the rate law for the overall reaction. And there's a reason for that, because the first step in this mechanism is what we call, let me change colors, the slow step. Slow, so I chose green like a turtle. That's the slow step. So, of course, in any process where you have a series of steps, the overall speed of the process can only be as fast as the slowest step, right? So, step 1 is the one that's determining the overall rate. Hence, why its rate law is the same as the rate law for the overall reaction, right? In other words, adding carbon monoxide has no effect on the rate because it doesn't matter how much carbon monoxide I have. It can only be used up as fast as I'm creating NO3, right? And NO3 is being created by the first step, which is slow. It's the bottleneck here, right? The process can only be as fast as its slowest step. Okay, so what is the lesson here? Okay, a couple things you need to get out of this. So let me just create a new. So here's a couple things you need to know from this. The first thing you need to know is that what makes a mechanism valid, okay? What is a valid mechanism? You may be asked someday in the near future to propose a mechanism for a reaction, okay? And what I would give you is I would give you the overall equation, okay? And I would give you the rate law, okay? So in order for a mechanism to be valid, two things need to happen, okay? The first thing that needs to happen is that the sum of each elementary step must, or each elementary step, adding them together, they must equal the overall equation. Okay, so you'll remember from the example I just gave, if you add up the two elementary steps, it equaled the overall equation, right? So that was the first thing that gave me a clue that my mechanism was valid. And the second thing that has to happen is that the rate law for your slow step must equal your overall rate law. Okay? The rate law for the overall equation. And guess what, guys? As long as your mechanism satisfies those two criteria, it's equally as valid as anybody's mechanism, actually. A mechanism cannot be proven, actually. There's no way to prove it. It can only be disproven. And the way to do that is to do a reaction and measure its rate law and see if the rate law for that reaction conforms with the rate law for your slowest step that you came up with. Okay. So, how might you think, you might be thinking, do we know how fast each elementary step is? Well, there is one general rule that you should know in regards to that, and that rule is that the probability of that collision happening determines how fast that step is. And when you have a situation where one thing is colliding with another thing, and there's only two particles involved, then that is called a bimolecular bimolecular step, meaning two particles are involved. And it'll be fairly quick because it's not too hard. It's to get two particles to collide in just the right way, right, comparatively. But if your elementary step involves the collision of three particles, keep in mind that an elementary step is a single collision event, meaning what you're saying by writing that elementary step is those three particles must collide simultaneously, three particles at once, in just the right way, right, with sufficient energy. And so that obviously is going to be an event that does not happen quite as often, because by the chance of getting those three different particles together to collide at the same time in just the right way is obviously going to be much lower than if there were only two particles involved. So this is called a make that an R, a termolecular step, right? Ter meaning three. And you can also have a unimolecular step, meaning it's just one particle decomposing, right? This would be unimolecular. And that can happen. It's a decomposition, right? It's just as you increase temperature, bonds are breaking. It's not really a collision that's happening when you have a unimolecular event. As a general rule, unimolecular steps are faster than bimolecular steps, and bimolecular steps are faster than termolecular steps. And that's all about probability, right? What's the probability that three things will collide all at once in just the right way? Termolecular steps are fairly rare, actually, and we generally avoid them when we're trying to come up with mechanisms because they're so rare. Most mechanisms are made out of bimolecular steps or unimolecular steps, okay? So let's take a look at a quick summary that I have of that for you. I'll give you a chance to copy it down. Okay. All right. So here's a quick summary that I have. Rate laws of elementary steps, right? So a unimolecular step is just one thing decomposing, and this is its rate law, right? It would be first order. Bimolecular, you can have two things colliding with each other that are the same, or you can have two different things colliding, right? Notice the difference in the rate law. Either way, it's second order overall, right? Because when you come up with the overall order, you add up the exponents. So both of these would be second order overall. And in termolecular, right, there's three different combinations. You could have three things all the same colliding with each other, which would be third order for that thing. You could have two things the same and one thing different, or you could have all different, right? Either way, these are all third order overall, okay? So what you're saying when a reaction is third order, right? So if you have a reaction whose overall equation ends up being, it's interesting. Wonder why it won't let me draw. Okay, well we'll just do a new one here now. Yeah, so if you have an equation whose overall, okay, now we're running into issues. Okay, we have a little bit of a hiccup here. Not really sure what's happening. All right, let's just close it out and open it again. Okay. All right. Sorry about this. Like I said, there's bound to be some hiccups. First time using it. There we go. We're back in business. So back to what we were talking about. If you have an equation that looks like this, A plus B yields C plus D, and you decide that the rate law for this is A squared, A second order times B first order, and it's third order overall. What you're actually saying is that this step, being third order overall, requires the simultaneous collision in an elementary step of two A particles and one B particle, right? So we would guess that this reaction would be quite slow overall because it's third order. The higher the order, generally the slower the reaction because of those reasons. So before we go, let's take a look at a couple of problems for this. Make sure that we can do them. Okay. So let's take a look at take a look at problem how to make this go away. Just close. There we go. Okay. All right. Let's make this black again. Okay, so let's look at number 10 here. Okay, so in number 10, they give us a reaction mechanism. Okay, and they ask us, what is the overall reaction? Is chlorine a catalyst or an intermediate, which we haven't covered? We'll cover it while we do this problem. What is the rate law of each of the elementary steps? And what is the rate law of the overall reaction? Okay, so let's start with A here. Okay, so what is the overall reaction? Okay, so what we're going to do is, let's just go ahead and paste this into the software here so I can just cross things out. Okay, so I'll just paste this into there. Okay, and make that a thing. Okay. All right. Except now I'm stuck again, and we don't know how to fix it. So if you give me a second, I'll figure this out. Let me just pause this and I'll come back after I've figured it out. Okay, I think I figured it out. Here's our problem, and it says what is the rate law what is the overall reaction? So I want you to look at this problem. There's two steps. We're proposing two elementary steps. And I want you to notice that what we have here is a situation where chlorine is being created in the first step and used in the second step, right? So that is an intermediate. Chlorine is an intermediate. So that answers B here. Chlorine is an intermediate because it's created in the first step and used in the second step. So the overall equation ends up being 2. Oops, that was not what I meant to do. Just erase that. So the overall equation ends up being 2 NO2Cl because you have one here that you're using in the first step, and you're using a second one here in the second step, plus nothing, right? That's it, it looks like. So let me just erase that plus. Sorry, that was my mistake. So 2 NO2Cl yields, looks like 2 NO2, so 2 NO2 plus Cl2, right? So there we go. There's the overall equation. The chlorines cancel out here. We're creating one NO2 molecule in the first step and a second one in the second step. And we're creating a chlorine molecule here. So there's our overall equations. There's our answer for A. Now let's take a look at C, since we already answered B. What is the rate law for each of the elementary steps? Okay, so the rate law, that's my dog, I'm sorry. The rate law for the first elementary step is rate is equal to K times the concentration of NO2Cl, and that's it, right? And the rate law for the second step is rate is equal to K times the concentration of NO2Cl, first order, times the concentration of chlorine, first order. Okay? All right. And part D says, what is the rate law for the overall equation, overall reaction? And we said earlier that that's going to have to be the rate law for the slow step. So the slow step is indicated to us as step number 1. So the overall equation is going to be, our overall rate law is just going to be K NO2Cl, and that's it. That will determine the rate for the overall equation. Okay. So let's talk about a catalyst now. We haven't talked about what catalysts are. It's the last thing to talk about in rate mechanisms, and we'll be done. So actually I lied. There's 2 more things to talk about in rate mechanisms, and then we'll be done. So let's talk about catalysts first. So I'm going to use this slide here to show you an example of a catalyst. Okay. So take a look at this equation on this slide. This is the equation for the, we lost it. There it is. This is the equation for the destruction of ozone. So O3 is ozone, and you might know about these things called chlorofluorocarbons, which the issue with those is that they actually release chlorine atoms into the atmosphere. And that's an issue because chlorine is what we call a catalyst, and a catalyst changes the pathway. Okay? It changes the pathway of a reaction mechanism, now that we know about mechanisms, to make it so that it can happen quicker. Right? So it introduces a new elementary step, essentially, that becomes the new slow step, right? Changes the mechanism, and that new slow step is now faster than what the old mechanism was. Okay? So here's an example. Normally, the destruction of ozone happens quite slowly, but when you introduce chlorine, this is what happens. You get one collision where it collides with an ozone molecule, so that's these 2 here, and then you get O2 and ClO. And then what happens is that ClO then goes back and collides with an oxygen atom and produces O2 and chlorine again. So you can see that we started with a chlorine atom and then we produce a chlorine atom. So overall, there's 0 consumption of chlorine. Okay? That's what makes it a catalyst. You can look at a mechanism and identify a catalyst because it's used in one step and then created again in another step. And so overall, when you write the overall equation, it's not part of the overall equation. Okay? Overall, it's not used whatsoever. So that's a catalyst. Compare that to an intermediate, which you can also see in this mechanism. You can see there's a ClO here being created and then a ClO being used. Intermediates are created and then used, whereas catalysts they start out in the beginning and they come back again in the end, right? So that's how you can tell the difference between an intermediate and a catalyst. And you can see the issue here, down here, is that it actually takes about 100 times this will happen before chlorine ends up reacting with something else to use it up. So chlorofluorocarbons are a big issue because they take a really long time. They have a really long half-life before they get used up in the atmosphere. And while they're up there, they're sitting there catalyzing the destruction of ozone, which is why we have a big hole in our ozone layer in Antarctica. So, okay. So that's catalysis. The very last thing we need to talk about is what happens when the intermediate, I think there's an example here. Okay. So what is it that happens when the intermediate is the slow step? Okay, as you can see in this particular equation. Okay, so let's take a look at this. I'm going to use my cursor here to kind of highlight what I'm talking about while I talk. So here's our overall equation. NO plus O2 yields 2NO2. And we can break this into two steps. The first step is one nitrogen monoxide colliding with an oxygen. It produces NO3. And then our second step is NO3 produces NO. Now, turns out that second step is our slow step. And that's a problem because remember we said earlier that the overall rate law has to equal the rate law of the slow step. But here's the problem. The slow step has an intermediate in it. And we can't have an intermediate in our overall rate law because intermediates are not reactants. And we can only have reactants in the rate law. So what are we going to do about this? Well, I want you to notice on this slide that this first reaction is reversible and fast, okay? Meaning it goes both ways. And that does something for us. Here's what that means. It means that this reaction reaches something called equilibrium. And at equilibrium, the forward reaction and the reverse reaction are going at the same rate. So in other words, the rate of the forward reaction, here's the rate law for the forward reaction, and the rate of the reverse reaction, here's the rate law for the reverse reaction, right, are going to be equal to each other. Okay? And we can use that to our advantage. Here's how. Now, I know this slide looks really messy. It's got a lot of stuff. So just listen to me as I break it down kind of step by step for you, okay? So what we're showing here is the rate law of the first reaction, and what we're showing here is the rate law of the reverse reaction, and we're setting them equal to each other. Because by definition, when they're at equilibrium, that's going to be true. Those two rates are going to be equal to each other, right? Now, what we're going to do is we're going to solve this little equation here for just that intermediate. That's the problem, okay? So we'll solve it for NO3, okay? And this is what we end up with. NO3 is equal to K1 over K negative 1, which is our two individual rate constants, okay? Rate constant for the forward and rate constant for the reverse, times NO and O2. Right? So we just solved. We just set them equal to each other and solved for the intermediate. So this was our intermediate. Now, what we can do is, since our slow step has that intermediate in it right here, and we can't have an intermediate in our overall rate law, what we're going to do is we're going to substitute this expression here that we solved for instead of instead of the intermediate. Okay, so we just took this up here and plugged it in down here. Now, look what we end up with. We're going to combine all of these k's here into one k, all right, because they're all constants anyways, so let's just make them one constant. And we're left with NO2 second order, O2 first order. And both of those are in my overall reaction. So I've just done a little trickery, a little magic here to create the overall rate law out of the slow step and not have to use an intermediate. And that, my friends, is the very last thing you need to know in regards to kinetics. So, hasta. I will see you guys after the winter break. I hope that this was helpful. Please comment on Edsby if you guys would like to have a Google Hangout, and you can ask me questions, and we can do that shortly before we come back. Okay, maybe that weekend of New Year's. So just let me know if you want to do that, and have a great winter break, guys.